This is lecture 28 of Condensed Matter Physics 1. And what we are going to do in this lecture is formalize the concept of phonons, and then in this week we are going to see how phonons interact and affect the properties of a system. So, to start with, what we did in the previous 2 or 3 lectures was that shown that if you have a collection of these atoms that form a crystal, there are well defined normal modes of oscillation in this, and we modeled it, and that model was enough to show us all the characteristics of this vibrations. So, what we have learnt about is the normal modes of vibrations of a crystal, and these are nothing but collective oscillations of all atoms. So, it is not that one atom is vibrating around, it is all collectively they vibrate, and we had seen that the way this collective oscillation is given is some amplitude e raised to I k dot r minus omega t, where in general omega depends on k, number 1. Number 2, the displacement shown has meaning only at r equals some integer j times r naught, where r naught is the primitive. Lattice vector. So, although I have written this in the travelling wave form, so even if I make a wave like this, the only place it is meaningful is at these points where the particles are. And therefore, we also saw, and I gave you this as a practice problem also, that you can also describe the same displacement through a different k. So, k is defined modulo g, where g is the reciprocal space vector. So, k, a given k within the Brillouin zone describes the same motion as k plus g. So, this is the kind of motion that atoms are performing, and then we use this used omega k to quantize the energies of each mode, and what we said is that the excitation energy is h cross omega k, and this then explained. Let me rewrite this. T cube behavior of C v as t goes to 0. We have done all that. What I want to do today is formalize today's agenda, if you will, to formalize the concept of this quanta of vibration. And if you have noticed, in the past 3 lectures I have not used the word phonon, and this I am going to call a phonon. When we do so, we also learn about how to manipulate the wave function or the properties of phonons. So, with this we will also learn about some rules to be followed when an outside particle, it could be a photon, it could be a neutron, and we will focus on these two, interacts with a crystal. And with the concept of phonon, this will be transformed into interaction between the external particle and phonons. So, that is the idea of formalizing the concept of phonon. We will develop some mathematics for it, and then I can transform all the interactions that neutrons or photons have with the lattice into the language of these phonons. Let me write this phonon better. Okay. So, with that background, let us look at the Hamiltonian and various quantities that we had. The Hamiltonian for the lattice within the model of that nearest neighbor interaction and harmonic approximation was given as 1/2 p jth site square plus 1/2 c, which was the constant of spring constant. I think also called it k 0, either one of them, times u j plus 1 minus u j square, and this whole thing is summed over j. This was the model we had taken. So, what we are doing is, I will just symbolically show it, that I am taking these atoms, I am just making one line. You can think of this as a plane also of atoms in direction perpendicular to the k we are talking about, and then the jth atom has displacement u j. So, next one is, this one is j plus 1th atom, this one is j minus 1th atom, and their displacements are u j minus 1, u j plus 1, and within this next nearest neighbor harmonic interaction, the potential energy u of the entire lattice is given as summation over j 1/2 k 0 or c u j plus 1 minus u j whole square, and p j is the momentum of that atom. So, now we want to write it in quantum mechanical form. What we want to show is this Hamiltonian is equivalent to a collection of harmonic oscillators. and along the way we are also going to quantize it. So, remember what was u j? U j as a function of t was given as some amplitude u, and I call this amplitude depending on the k. Let me write this as a vector e raised to I k dot r minus omega t. And as I said, r is nothing but the j times the primitive vector. So, I can write this as u k e raised to I k dot j r 0, and j is not a vector, r naught is a vector, j is the site, minus omega t, and this will be summed over k. So, if you like, this is like each individual mode. So, u k e raised to I k dot r 0, let me write j separately, minus omega, which depends on k t, is a particular mode, displacement, and the general displacement of the atom at j site is a linear combination of all these, and each one is with amplitude k. So, in a way what we are doing is writing a Fourier expansion of the general displacement. So, what I have for this is the jth site t, and let me now go to 1D, because I do not want to get involved in that writing the vector sign all the time, but it can be easily generalized. So, this is u k, the amplitude for the kth mode, e raised to I k r 0 j minus omega k t, the general displacement. And to go to quantum mechanics, what I will do is I will first look at the stationary solution, that is without t. So, that will be u j equals summation u k e raised to I k r naught j, and then replace u k, which is the amplitude, by an operator q k. So, I am just distinguishing, I mean classically q k is nothing but the generalized displacement. So, I define u j equals summation q k e raised to I k r naught j, and sum is over k, and q k is an operator. In general, then since this is each mode, you can easily see by superposition u j t is going to be equal to summation k q k e raised to I k r naught j minus omega k t. So, I have just taken the stationary part and define it like this. In the same manner, if I take the Fourier transform, the q k operator is going to be equal to summation. For normalization, let me also write divide by proper terms. So, let me write this first and then we will come to that. U j e raised to minus I k r naught j, that is about it. And now, let us properly normalize it, proper normalization, just like we do in Fourier transform. I am going to write then u j equals 1 over square root of n. So, it is clear that I am doing periodic boundary conditions over cell of n cells, summation k q k e raised to I k r naught j, and inverse Fourier transform q k is 1 over root n summation over all these sites j varying from 0 to n minus 1 u j e raised to minus I k r naught j. And in the same manner, let me define the corresponding momentum operator p k, and you will see there is a subtle difference. This is going to be 1 over square root of n summation j equals 0 to n minus 1 p j e raised to plus I k r naught j. Why we take this plus is so that all the commutation relations are satisfied properly. So, let us see that. So, I have q k, the quantum mechanical operator, as 1 over root n summation u j e raised to minus I k r naught j, and p k equals 1 over root n summation p j, j equals 0 to n minus 1, j equals 0 to n minus 1 e raised to plus I k r naught j. In case you are wondering what r naught etcetera are, so let me just make this again. The lattice is like this, and this distance is r naught. Let us take the commutation relation. Let us take q k p k commutation relation. This is going to be equal to 1 over n when I multiply summation j equals 0 to n minus 1 summation L equals 0 to n minus 1. I am going to have u j p L e raised to minus I k r naught j plus L. Let us see, am I getting the things correctly? No. Let me rewrite this. This is going to be e raised to minus I k r naught j plus minus L. Now, we can do some summation. Let us see now, is there a k summation somewhere? No, there is no k summation. So, this is q k p k. Now, you can see that this is going to be 0 summation e raised to minus I k r naught j minus L sum over j and L. K, let me remind you, is nothing but 2 pi over n times sum n. So, this is going to be 0 if j is not equal to L. So, what this gives me, and this you can check very easily by summing like a geometric series, that this is going to be equal to 1 over n, is this whole thing, summation j equals 0 to n minus 1, summation L equals 0 to n minus 1. U j p L is I h cross delta j L, and then I have e raised to minus I k R naught j minus L. I sum over L, this is going to be 1 over n summation j equals 0 to n minus 1. Delta JL forces this to be that j be equal to L. So, I h cross times 1, and this is nothing but n I h cross over n. This cancels and this is I h cross. So, what we have established is that q k p k commutation relation gives me I h cross, if k is the same. Now, I have been saying that when j is not equal to L, this summation of exponential is going to be 0, and that is going to be useful if I sum, if I take the commutation relation between q k and p k prime. So, let us do that now. So, this is established. Now, let us do commutation relation q k p k prime. I am doing it separately, so that you see it clearly, and k is now not equal to k prime. This is going to be equal to again 1 over n summation j equals 0 to n minus 1 summation L equals 0 to n minus 1 u j p L e raised to minus I k j e raised to plus I k prime L, and k is not equal to k prime. So, this is equal to 1 over n summation j equals 0 to n minus 1 summation L equals 0 to n minus 1 u j p L is again delta j L, and I get e raised to minus I k j e raised to I k prime L. Again, j is going to be equal to L because of the delta function. So, this I can write as 1 over n summation j equals 0 to n minus 1, and the L 1 goes away, I h cross e raised to minus I k minus k prime j. Remember, k is equal to 2 pi over n times some n equals 0 plus minus 1 and so on, and k prime is 2 pi over n prime, n equals 0, n prime plus minus 1 plus minus 2 and so on, and this goes all the way up to Brillouin zone. So, you do this summation, and for n not equal to n prime, you are going to get this summation j equals 0 to n minus 1 e raised to I k minus k prime j equals 0. So, you get q k p k prime equals 0 for k not equal to k prime. And what this means is, you combine the previous one with that, q k p k prime is equal to I h cross delta k k prime. And these are the commutation relation. Between displacement q k and momentum p k operator. So, we have defined collective q k and p k operators for this system, all right, and now what we can do is use these to write the Hamiltonian. So, our Hamiltonian, recall, is nothing but h equals summation j p j square over 2 m plus 1 half k 0 summation u j plus 1 minus u j whole square. It is a quadratic Hamiltonian, harmonic Hamiltonian. Oh, before I go further, I want you to show something. Show that the potential energy summation j 1 half k 0 u j plus 1 minus u j square gives the correct force for jth particle. So, now what we can do is I substitute P j equals summation P k e raised to, remember the sign is opposite, minus k r 0 j summed over k, and u j equals summation k q k e raised to I k r 0 j. You substitute this in, and what you get after some manipulation, and this I am leaving for you as an exercise, you are going to get this as equal to summation k 1 over 2 m p k p minus k plus 1/2 m omega square q k q minus k, where omega square is what we had derived in lecture 25. This is equal to 4 k 0 sine square k a by 2. So, I am leaving this for you. I will just give you some steps. For example, when you write u j plus 1 minus u j, this is going to be equal to q k e raised to I k j plus 1 r 0 minus q k e raised to I k j r 0 summed over k. And what you get from here is summation over k q k e raised to I k r 0 minus 1 e raised to I k j r 0. When you square it and sum it, you are going to use along the way the identity that summation e raised to I k j minus L r 0 summed over k is going to be proportional to delta j L, or this is going to be equal to n delta j L. So, along the way you use these and then you show this. So, what you have managed to do now through all these definitions, where we wrote u j equals summation k 1 over root n q k e raised to I k r naught j, and p j equals 1 over root n summation over k p k e raised to minus I k r naught j, where k is equal to 0 plus minus 1 plus minus 2 and so on, 2 pi over n, and the sum is over the Brillouin zone. What we have managed to do is write h equals summation over k 1 over 2 m p k p minus k plus 1/2 m omega square q k q minus k. So, this is equivalent to collection of harmonic oscillators, each with the Hamiltonian one over 2 m p k p minus k plus 1/2 m omega square q k q minus k. You have added that. So, this whole thing, this collective oscillation is like a collection of harmonic oscillators, each with its own frequency. And how many harmonic oscillators? N of them, if we are doing it over n cells. Now, what we are going to do is make a transformation to creation and annihilation operators, because that will make things very easy. We are going to now define operators that will create an excitation of frequency omega and with a good quantum number k, and we will see what that k signifies, and also annihilate it, just like we did in quantum mechanics. Recall quantum mechanics chapter on harmonic oscillator. So, you define, and I am going to just go over it quickly, the rest I will leave for you to go back to your quantum mechanics book and see. Q k equals the square root of h cross over 2 m omega k a k plus a minus k dagger, and I am going to define p k equals the square root of h cross m omega k by 2, there is a 1 over I can write a minus k minus a k dagger. This is how I am going to define these operators, and they are defined in this particular way, so that they have specific properties. And what are the properties? We will see in a minute. Then you can write this Hamiltonian as summation k a k dagger a k plus a half, where k is over the Brillouin zone, and this defines the phonon states in number space. So, I can define a vector n, just like we do in harmonic oscillator, on which if a k acts, this gives you square root of n minus 1. So, it destroys a phonon. A k dagger acts on n, this gives you square root of n plus 1, and let me specify this to be n k, so that it is clear that this is the number of phonons in the kth mode, and a k dagger, a k is the number operator, it gives you n k. So, n k is the eigenstate of the Hamiltonian, and it signifies n k signifies nth excited state of harmonic oscillator with good quantum number k. So, the energy is n k plus a half h cross omega. So, this we also say is that the state has n k phonons, exactly like we do in electromagnetic theory, that there are n photons. Now, we are saying n phonons. So, if you like, if you make a picture of this crystal, what this is collection of these phonons. This is the kind of picture we have made, and this may be a phonon with good quantum number k, 1 let us say, the other one could be k 2 and their number could be n k 1, this could be n k 2. So, I am thinking of this not as these individual atoms vibrating back and forth, but these phonons whizzing around, and if you like in Debye model their speed is v sound, but just as an example. Otherwise, we have this and each one has its own frequency, omega k 1, omega k 2 and so on. So, they are all moving around. So, they are like particles of this mechanical vibration, just like photons are particles of electromagnetic vibration. We have this crystal which is filled with these phonons which are moving around, and these are particles of excitations of these mechanical vibrations. So, that is the picture that we have made. Now, we can use this to learn about what happens when a particle interacts with a lattice. So, before I do that, let me just summarize what we did. So, we looked at the Hamiltonian of a crystal within the harmonic approximation and nearest neighbor interaction, and then wrote this in quantum mechanical form by defining operators q k, which is summation j u j e raised to I minus I k j r 0, and p k, which is summation j p j e raised to plus I k j r 0. And then we could write the Hamiltonian and think of the crystal as a collection of harmonic oscillators a k dagger a k plus a half h cross omega k, where a k dagger and a k are defined in terms of q k, such that q k is equal to square root of h cross over 2 m omega k a k plus a minus k dagger, and p k is equal to 1 over I square root of 1 over h cross m omega k divided by 2 a minus k minus a k dagger. So, that is what we have learnt. One question I can ask now is question, is k, and in 3D it will be k vector, related to momentum of a phonon or momentum of the lattice. And what does it mean? Well, usually when you look at free particles and write a wave function like e raised to I k dot r, that k is related to the momentum. So, is that the case here also? What I am going to show you is that this k does behave like momentum, but it is not the momentum, and it is related to something else. The physical phenomena is something called the phase matching of waves. So, for that, what I like you to do is take a crystal, again working in one dimensions, look at the displacement of each atom and show that the total momentum of the crystal, which will be defined as summation m u j dot vanishes. So, when this is vibrating, there is actually no momentum, the net momentum is 0, but yet you will see that this k that we have associated as a good quantum number to each phonon is going to behave like momentum, and that comes when we consider scattering of a particle from the crystal. So, that is what I am going to consider next, scattering of a particle from a crystal, and that is where all this formal development that we wrote comes in handy. So, what we are going to say is that when there is a particle which is coming in, right. So, this particle is external, to the crystal. So, what we are considering, here is this crystal and there is a particle that comes in with some de Broglie wave e raised to I k dot r and gets scattered and goes out with e raised to I k prime dot r. And we want to know what is the probability of this happening and under what conditions does this happen. That is the problem. And what is it getting scattered by? It is getting scattered by either these, certainly by these atoms in the crystal, or equivalently what I said earlier, these phonons whizzing around here. So, this particle comes in, collides with a phonon and then gets scattered. That is how we are going to picture this. So, let us see how we do that. So, first I write the Hamiltonian for the collective system. This is going to be P j square over 2 m, the ion kinetic energy, plus 1/2 k 0 u j plus 1 minus u j square. This is the original Hamiltonian, plus the Hamiltonian for the particle, which is like the free particle Hamiltonian, plus the interaction. So, let us write this V interaction. The particle interacts with particle at j minus u at j, summed over j. So, let us picture this. Here is this crystal. Here is the particle coming in. It is at a position r. Its Hamiltonian is p square over 2 m of the particle. The atoms inside are vibrating with that u j, and there is an interaction energy between this particle and the jth particle, and this is what I am calling V interaction, depends on r minus r j minus it has displaced by u j. And what the initial state is, the initial state before the interaction of the system is e raised to I k dot r, that is the wave function for the particle coming in, times n, let us say q. where q is the q for the phonon and n is the number of phonons. So, n q is the number of phonons with wave vector q, and the final state is some e raised to I k prime dot r n prime q. And we will see how they are related. So, if I look at this is going to be related through the Hamiltonian of the potential of the interaction. If I look at V interaction, this is equal to summation over j V r minus r j minus u j. I am writing this as vectors, and this is going to be equal to, if I expand this, summation j V r minus r j plus summation grad of V at r minus r j dot of u j. Therefore, there will be a minus sign plus higher order. And to understand what is the transition probability, what I got to do is take the expectation value of e raised to expectation value of e raised to I k dot r, this is k prime, and let me in general write this as q prime and prime V interaction e raised to I k dot r n q. Okay. Now, let us take both terms one by one. So, if I look at the term V r minus r j summed over j, this is a periodic potential. And if I take its expectation value e raised to I k prime dot r some n prime q prime V interaction, this only this r minus r j term summed over j e raised to I k dot r n q. This is like scattering from a periodic potential. Why? Because n prime q prime n q will give you delta n n prime delta q q prime, and that means no change in phonon state, neither is created, nothing happens. This is like a static lattice, and this e raised to I k prime dot r V periodic e raised to I, this is k prime k dot r, will give you delta k is equal to g, the Laue condition. So, in this static approximation where there is nothing moving, this is a fixed periodic potential, you get either X-ray diffraction if the incoming particle is a photon or X-rays. If incoming particle is a neutron, you get elastic neutron scattering. So, this is that, and that we have covered in detail. Let us look at the second term. The second term is sum over j grad of V r minus r j. I am writing this symbolically that this grad is created at that point, dotted with u j, where u j is the displacement at jth site. Which I can write as summation j summation q grad of r minus r j u q, this is a vector, dot u q e raised to I q r naught j, q dot r naught j. Writing it in 3D. I mean, as I said earlier, I have shown this in 1D, but generalization is quite easy. Now, this is some function, some vector function of r minus r j is r naught j. And this depends only on j. This is the only term depends on j, and this is the other term that depends on j. So, I can write this term as equal to summation q u q dotted with, I can sum over j, some function of r minus r j e raised to I q dot r naught j. And I am going to now do a manipulation. So, summation j f r minus r j e raised to I q dot r naught j, I can write as summation j f of r minus r j, r naught j is r j, e raised to I minus I q dot r minus r j and multiply by e raised to I q dot r. So, that e raised to I q dot r cancels. This part I put in extra and this will cancel. But then advantage of doing this is that I can write this as e raised to I q dot r summation j, some function of r j e raised to minus I q dot r minus r j, same quantity. So, this can be written as that f q. This is like the Fourier transform, and therefore, this term here becomes summation q u q f q, again let us write the vector signs, e raised to I q dot r up to the first order in u q. Now, let us take the expectation value. If I take the expectation value of e raised to I k prime dot r n q prime n prime, then I have here summation q u q f q e raised to I q dot r, and on this side let me write e raised to I k dot r n, let me write this n q double prime. Remember, u q was replaced by q q in quantum mechanics, quantum mechanical treatment, and this was equal to that constant 1 over 2 h cross over 2 m omega q a q, sorry, a is the operator, a q plus a minus q dagger. So, all this then comes out to be proportional to, let me write this as integral e raised to minus I k prime minus q plus, or that will be also minus, k dot r, and with that I will have the term a q, this is proportional to, and then I will have the term a q with n some q double prime and q prime, and I will have a second term plus integral e raised to minus I k prime plus q minus k. I have made it plus q because I am going to change the a q part to a plus q dagger n q double prime n prime q prime, and rest are all constants. Now, you see that the first term this one is, when I integrate over 0, it gives you that k prime should be equal to q plus k, and n q prime should be equal to n q double prime minus 1, and q prime equals q double prime. In fact, it is going to be equal to q, because that is the operator, that is the only place it will work. So, what has happened is there is a neutron of, or any particle of momentum k coming in, and it gives rise to an outgoing particle of k prime momentum, and that k prime is equal to k plus q, and also the n q prime or n q has gone down by 1. So, that means a phonon was absorbed such that the outgoing energy had momentum k prime equals k plus q, and energy which is also added because this phonon has been destroyed. In exactly the same manner, the second term here will give you creation of a phonon. So, let me just make it more clear in the next page. When you look at these matrix elements, and I will just look at the phonon destroyed part, what you had was k prime going out is k plus q, and energy of outgoing particle is going to be a k plus epsilon of q, which is E k plus h bar omega of q. This is like momentum conservation. As if this phonon had momentum h cross q, but it is not the real momentum, it is like the momentum. Okay. And the second term is energy conservation. So, this phonon has been destroyed, it gave its momentum to the incoming particle, it gave its energy to the incoming particle, and outgoing particle has this new momentum and new energy. Notice one more thing, when we looked at this matrix element, I had written u j equals summation q k or q e raised to I q dot r j. I could equally well have written this as summation q q e raised to I q plus some reciprocal vector g r j. So, this relationship could also be k prime equals k plus q plus some g. So, this is the general sum rule for scattering by one phonon. So, k is conserved only up to a g, you can always add and subtract g. This is similar to elastic scattering, where k prime was equal to k plus g. So, the k of incoming and outgoing particle could differ by g, the Laue condition. In an inelastic collision, in addition to that g, you also have the momentum of the phonon created. You can work out the other part yourself. So, what we have shown is that having defined the phonons in a particular, through properly through quantum mechanical treatment, we could take the transition matrix element and show how the q of phonon affects the incoming and outgoing momenta of a particle interacting with the lattice. This we will use in the next lecture to describe neutron scattering and light scattering, inelastic light scattering from crystals that give us information about the phonon dispersion curve. So, let me now conclude this lecture by stating that quantum mechanical treatment of crystal vibrations has been done, and what it shows you is that the Hamiltonian for the vibrating crystal in harmonic approximation can be written in terms of creation and annihilation. Operators, and then finally some rules, and there are two of them: momentum and energy conservation. For scattering of particles from a lattice have been worked out up to the first order in displacement. Thank you.